And therefore, the ultra-wideband signals is not influenced by clots, and then we don't have the need of put the electrodes in contact with the skin. But we can put the antenna over the clots. And the last advance of the CMOS technologies allow low cost and high miniaturization of this device. So we can use the device very small, which can be easily integrated into the wearable, into a garment. The rationale for biomedical applications is related to the mechanism that is based on the differential electromagnetic impedance between different layers of biological tissues encountered by the signals starting from the thorax, for example, towards the heart. So the electromagnetic wave crosses, starting from the air, crosses fat layer, muscles, cartilage, lung, heart. And then we have the same path but behind. And from the overall this path, forward and behind, is produce an attenuation of the signal. And for example, the impedance of cardiac muscles is in the order of 60 ohms. The impedance of blood is about 50 ohms. So it can be expected that a roughly 10% reflection magnitude of the radio frequency at the interface between the muscles and the blood. So the heart and the blood. These allow us to identify the nature of the heart by measuring the reflection magnitude of the radio frequency. And by estimating the time delay, we can measure the position of the heart, and then in dynamic terms, we can identify the movement of the heart wall. Here we have the idea is to realize that we are doing that, is to integrate into a single silicon die the low power radio, the low power supply, and the radio frequency sensor. In this case, and the antenna should be integrated, the antenna should be placed on the garment and connected to this chip. The block diagram of the fully integrated ultra-wide radar is represented here. We have the microcontroller which drive a pulse generator. An impulse is generated, is produced, it travels towards the heart, and then it is bounced off and captured by the receiver antenna. The signal is amplified by a low noise amplifier, and then here it is used cross-correlation strategy. So the signals, the output of the low noise amplifier is multiplied by the same pulse transmitted but delayed and shaped. And here we have the maximum of the correlation when the shape of the signals of the pulse transmitted and generated, okay, and captured is the same. And an important parameter is the delay. By modifying the delay, we can optimize the output of the multiplier. And then the output of the integrator. The integrator is very important in order to bring the signals at base band, in order to be processed, in order to detect information about the motion of the wall, the heart wall. Here we have the cards, but they are the results of simulations. We have the Gaussian monocycles pulse at the output of the antenna. Here we have the signals, the simulated signals at the output of the integrator. This is an application, the outer garments from the project Proetex, whose coordinator is Annalisa, who will talk after me. The idea is to use this technology in order to put this antenna on the jacket of the fireman, and in order to detect the information related to cardiopulmonary activity, such as the heartbeat and the breathing frequency. A challenging application, but I think it can be realized in a far future, is to use this technology in order to detect the arc of the aorta distension, in order to non-invasively record the blood pressure. Currently the blood pressure monitoring device work not in real time, but are basically very invasive. This could be a challenging application for this task. Another crucial aspect of this technology is the antenna. A possibility is to realize the antenna onto textile substrates in order to be integrated completely into a garment. By results of a simulation, it can be feasible, and we are working towards this direction. Possible electronics antenna placement, of course, the electronics should be very small as possible in order to not affect the movement, the free movement of the subjects, so that it should be very comfortable for the subject wearing it. In conclusion, the ultrasound system was able to acquire cardiac low frequency signals and ultrasound investigation. The ultra-wideband system, we basically did a feasibility study from theoretical analysis and CAD tool simulation. But it's a very promising technology because the recent advances in silicon CMOS technology allow the realization of a miniaturized system on a chip sensors. But we have the crucial issues to be addressed. As for ultrasound system, we have to solve the problem related to the good. Okay. We have the ultrasound system. We are the problem of the contact between the electrodes and the skin. So the adherence the mismatching of the electrodes of the skin is very important, and during this is affected by motion artifacts, and this is very important. So and in order to use also when in a clinical environment, the operator should be very able to make an echocardiograph. So a wearable monitoring system based on this principle is very, very crucial. Concerning the ultra-wideband system, is very promising, and we did simulations. We did some simulation experiments, and the idea is to perform this, to realize the chip containing the transmitter and the receiver, the transceiver of the ultra-wideband, and the uses that on human subjects. Thank you very much.